Hello everyone, I'm going to present a poster for International Materials Research Congress, named as Graphene Oxide Functionalized with Cysteamine by a THIOL-ENE click reaction for the growth of metal-organic frameworks. The functionalization of graphene oxide has been one of the topics of interest in recent years due to the improved performance in different applications. When graphene undergoes the oxidation process to obtain graphene oxide, many defects are generated in the sheets, obtaining more alkene groups. Taking advantage of this, thiol-ene click reactions are a powerful alternative for the orthogonal functionalization of graphene oxide sheets under mild conditions, obtaining high reaction yields and avoiding the formation of byproducts, maintaining availability of the oxygenated group of graphene oxide for their utilization as, for example, in the growth of metal-organic frameworks. Metal-organic frameworks are a three-dimensional material composed by anorganic ligands coordinated to metal clusters, resulting in crystal structure, which can be used for various applications such as biosensing, drug delivery, gas capture, batteries, among others. In this work, the orthogonal functionalization of graphene oxide with cysteamine is proposed using a thiol-ene click reaction, keeping the oxygenating groups to subsequently perform the in situ growth of zinc-based MOF. By having a functionalized material, it will allow the growth of crystalline network on it, obtaining greater stability and availability of metal-organic framework in various applications. The method consists in using graphene oxide previously synthesized with cysteamine and a photoinitiator, which is a solution irradiated with ultraviolet light. After a certain time, the material was washed and a solution of metal salt was added to ensure the coordination of the metal clusters in the oxygenated groups of graphene oxide and the added amine groups from cysteamine. Then this solution was poured into a Teflon-lined autoclave with a solution of trimesic acid. The reactor was heated, and once it was cooled, the final material was washed and recovered to perform the characterization. The same methodology was carried out using graphene oxide without cysteamine. The results obtained by FTR show in the sample graphene oxide cyst a band in 1616 corresponding to the interaction between the thiol group and the alkene groups of the graphene oxide, indicating a successful bond. Also at 106045, the band of the amine group is shown. Once the metal-organic framework was grown, bands between 1330 and 1650 appears, corresponding to the asymmetric and symmetric vibrations of carbonic groups in the metal-organic framework. The high-resolution spectra of sulfur 2p and nitrogen 1s of the graphene oxide and graphene oxide cysteamine sample was shown in figure 2a. In sulfur 2p of graphene oxide cysteamine, different bands are shown around 162.5 and 164 electrovolts, corresponding to the bonds between carbon and sulfur. In figure 2b, in oxygen 1s, a band is shown around 530 electrovolts, indicating the the existence of a coordination of the oxygen and the zinc metal. Also in nitrogen 1s, a band around 400 electrovolts appears due to the interaction of the metal and the amine groups of cysteamine. In the sample without cysteamine, it is not possible to see this band. The elemental analysis obtained by XPS shows an increase in the atomic percent of sulfurum in the graphene oxide cysteamine sample. Due to the presence of cysteamine, the sample case with nitrogen, the same case with nitrogen. Furthermore, the atomic percent of zinc in the sample, graphene oxide cysteamine, zinc metalorganic framework reaches at 11.68% compared to the sample without cysteamine. This is 5.49%. This can be attributed to the added coordination points in the graphene oxide cysteamine sample.